Good afternoon. Okay, so what I'd like to do today is move on to centrifugal separators. We're still focused on primary particle removal. We looked at gravity settling on Monday, and hopefully you found the lecture on vapor intrusion informative and interesting. So moving on, looking at an additional process, let's look at centrifugal separators. So centrifugal separators are among the most widely used particle collection device. What you see in the photo right here, the cone-shaped device with a tube, that's the centrifugal separator. It's a relatively small unit, and to give you a range of the size, they can be multi-story. So in terms of the flow that they can treat very small flows within, for instance, a shop where you have metal shavings, where you have wood shavings, to something that is multi-story, for instance, with a power plant or a manufacturing facility. They're used because they're simple, low capital cost. They have no mechanical parts, and what we're using with these is centrifugal force. They can operate at high temperatures. And you'll see with some of the other devices that we'll talk about, operating at high temperatures can be problematic. Because of this, and they can handle both liquids, they can handle dry materials, they can be manufactured to withstand harsh operating conditions, but generally they're not adequate alone to meet strict air pollution regulations. So in that case, they'd be used as a pre-cleaner before a more expensive device, typically have a relatively small footprint, and can be used for recovery and reuse of materials. So for instance, you saw that in the video by the Chemical Safety Board, where they were using the centrifugal separator to remove the aluminum shavings and particles, which then could be recycled. Can be used in petroleum refinery to recover catalysts, and can even be used in production of freeze-dried coffee to recover the coffee. Disadvantage is that they have low efficiencies, especially for smaller particles. So we'll go through a set of calculations so you can see that. They also have high operating costs due to the pressure drop, and they're unable to process sticky materials. So tar-like materials, what we call hygroscopic materials, things that are gelatinous. Those stick to the walls of the centrifugal separator, and therefore you don't get the removal, and they just simply clog up the unit. So when we talk about centrifugal separators, we have two different types. What is referred to as an involute cyclone separator, and that's what you see here. And the air comes in here. Basically there's a series of turns that it makes that causes the air to make these turns through the centrifugal separator. Now what happens is the particles that are in the airstream can't stay with the airstream, and they actually will deviate off, hit the wall, and then fall down into a hopper below. You can see that more in this image. I'm just going to switch to the highlighter. So the air comes in. This is a vein and axial. So it comes in. There's a series of veins that cause the airflow to make this circular pattern, and the clean air then flows up the top and out this way. The particles, on the other hand, let's go back and use the pen, and the particles here deviate from the path, hit the wall, so they're unable to stay with the path. They deviate, hit the wall, and then will fall down into a hopper below. It's just another image of a vane axial separator, and you can see the veins here. And so as the air moves in, these veins are causing the air to make this circular pattern through the centrifugal separator. Now, what you see is that in terms of, look at a conventional cyclone separator, for large particles greater than about 40 microns in size, we can get significant removals, greater than 95%. And you can see that as the particle size decreases, the removal efficiencies also decrease. We'll talk about high efficiency cyclones and what the difference is, but there you see even greater removals, and you can see the same thing on this figure here. So for instance, if you look at a 20 micron particle with a conventional centrifugal separator, we can get maybe about 82% removal. If we use a high efficiency centrifugal separator, we can get at 92%. So we can get significant greater removals. The problem is it's going to cost us more. It's going to cost us more in terms of operating costs because the pressure differential across the unit will be greater. And you can see as the particle size decreases, the efficiency decreases, and it's clear on this figure here. And let's look at how both the properties of the particle, the properties of the cyclone, and the properties of the gas affect the removal. So what we're looking at is as the parameter increases, so as particle size increases, you saw in the previous figure that the efficiency increases. As particle density increases, how would you expect that to affect efficiency? So as density increases, how would you expect that to impact efficiency? Think about, you have these particle gas stream. Okay. So as density increases, will that make it easier or harder for that particle to remain within that gas stream? So as density increases, it's going to make it harder, exactly. So it's going to make, as density increases, it makes it harder for the particle to stay within the gas stream, which means that it's more likely to hit the wall, which means that efficiency increases or decreases. It increases, exactly. With dust density, typically, as dust density increases, your efficiency increases, but to a point. So for instance, if the dust loading is high, then you're more likely to have particles hit one another, which means they have trouble staying in that flow path. Also, if they hit one another, they may aggregate to form a larger particle, which then has a more difficult time staying within the flow path and therefore is removed. Now, as the body diameter of the cyclone, so if we go back and we look at our cyclone here, so the body diameter is the diameter, so this is the body diameter. So as body diameter increases, efficiency decreases. As the ratio of the body length to the diameter increases, so let's look back. So if the ratio of the body length, so we're looking at the ratio of body length to diameter. As that increases, how would you expect that to affect efficiency? Let's just keep the diameter constant. Keep the diameter constant at 1, we increase the body length. What will that do?
Increase efficiency.
Increases in efficiency. Why? Try.
More surface area to get clogged up on.
Okay, there's more surface area. There's also more turns. The longer we make this, the more turns that airflow is going to have to make. The more turns that airflow makes, the more opportunity for that particle to deviate from the flow path and do exactly what you said. And it hits the wall and therefore gets removed. As the smoothness of the wall increases, your efficiency increases, and that's really, think of that in its efficiency of removal or recovery. You're going to get more of that material sliding down. It's not going to stick to the sides of the wall, and you'll have more material to recover. As the inner duct area increases, you get lower removal, which similarly, as the exit pipe diameter increases, you also get a decrease. Now, if we look at the gases, so now we've looked at the particles, the cyclone itself, and now we're looking at the gas. So viscosity increases as temperature increases. So as viscosity increases, how do you think efficiency is affected? It's going to decrease. So as temperature increases, as viscosity increases, your removal efficiency will decrease. As density increases, your efficiency also decreases, but it's viscosity that is the predominant effect. Density of the gas will have very little effect because if you remember, the density of your particle is so much greater than the density of the gas. And then if we look at the inlet gas velocity, as that increases, the efficiency also increases, but again, only to a point. We can compare gravitational force with centrifugal. So gravitational force is equal to mass times gravitational acceleration, and centrifugal force is equal to mv squared over the radius. So for instance, if we have a particle in a gas stream, and the velocity of that gas stream is equal to 18 meters per second, and the radius of the centrifugal separator is 0.3 meters. We'll just take it for that condition there, which is reasonable. So the centrifugal force over the gravitational force is equal to mv squared over R divided by mg. And mass cancels, because it's in both equations, and we have 18 meters per second squared divided by the radius, 0.3 meters, and we'll divide that by gravitational acceleration, and that is equal to about 110. So in terms of force, the gravitational force is about, under these conditions, about 100 times greater than the centrifugal force is about 100 times greater than the gravitational force. It's for that reason that we use centrifugal separators. Remember, again, thinking back to the video I showed on Monday, you had a gravity settler, the drop box first, followed by the centrifugal separator. So they were removing the larger particles in the gravity settler and the smaller particles in the centrifugal separator. If you tried to remove the same size particles in the gravity settler that you were removing in the centrifugal separator, you'd need a much, much greater area or volume of your gravity settler. So that's why we use centrifugal separators. We can determine the efficiency of these systems using this equation here. So efficiency, as we've kind of talked through the parameters that affect efficiency, now we can quantify this. So N sub E is the number of turns that the air is making as it moves down the centrifugal separator. V sub I is the velocity as it enters the centrifugal separator. So it's your flow rate divided by the height of the inlet times the width of the inlet. And so notice, just as we talked about, as N increases, as body length increases, efficiency increases. As velocity increases, the efficiency will increase. As the diameter of the particle increases, efficiency will increase to the square of that diameter. So diameter will play a significant role. Density of the particle, density of the gas will typically be much, much lower by several orders of magnitude. And that's why I said density of the gas will not play a very significant role on the efficiency, but temperature will play a significant role on the absolute viscosity. And then the width. So as we increase width, we decrease the efficiency. So if we want to increase the efficiency, we want narrow inlets so small width, and that reduces the distance traveled by the dust to the wall, and that actually increases your collection efficiency. We want a small body diameter. So the body diameter is this distance right here. And those will have higher forces than a larger diameter. So a higher gravitational force, and you'll get better removal. And then we want a smooth transition. So we want a smooth transition both as that air enters, we want a smooth transition from the body to the cone, and we want a smooth transition into the outlet. The previous equation was for plug flow. However, if we have mixing within the system, so we have mixed flow, then we use a similar equation to what we used previously, and we just take 1 minus the exponent. So we have mixing here in the system. So let's look at an example here. We have a cyclone separator, and it's operating at ambient conditions. It has an inlet width of 0.15 meters, a horizontal gas velocity of 20 meters per second. The number of turns is 5. And what we want to do is we want to calculate the efficiency for collecting particles of varying size. All of the particles have the same density of 2,000 kilograms per cubic meter. We'll operate at room temperature. So the dynamic viscosity is 1.86 times 10 to the minus 5 kilograms per meter second, and the density is 1.18 kilograms per meter cube. So that's the viscosity and the density of the gas stream. Just provided all of the data here in a written form. It's just the data that I just provided. And the efficiency for a plug flow system is equal to pi n sub e v sub I dp squared, density of the particle minus density of the gas, divided by 2 wi, the width times the viscosity. So for a 10 micron size particle, the efficiency using the plug flow equation is equal to pi times 5 times 20 meters per second. Make sure your diameter of your particle is in meters. So it's given in microns. 2,000 minus 1.18, and that is kilograms per meter cubed, so density. And we'll divide that by 2 times the width, which was given as 0.15 meters, times the absolute viscosity, and that is equal to, if we do the math, it's equal to 2.5. Now, your efficiency is a fractional efficiency. Can I have an efficiency of 2.5? No, absolutely. Okay, so if you get a numerical answer greater than 1, what is the efficiency? So the efficiency is 1 or 100%. Wherever your homework problems, where you get an efficiency greater than 1, non-kappa problems are coded that the answer is 1 or 100%. So with fractional value would be 1. If it asks for a percentage, it would be at 100. So for instance, if we look at for the 6.25 micron, everything is the same except, and I forgot the squared term here. So everything is the same except the diameter. So there, for the 6.2 microns, the numerical answer that you will get is 0.15. 977. So that corresponds to 97.7%. For the 5 microns, same equation. The only difference is, again, the diameter of the particle, and you will get 0.625 or 62.5%. And then for the 1 micron, the efficiency is 0.025, so it's 2.5%. So you can see, as we decrease the efficiency, as we decrease the size of the particle from 10 down to 1, we go from, under these conditions here, plug flow, we go from calculating an efficiency of 100% to calculating an efficiency of 2.5%. So you can see the significant impact. Now, if we want to calculate it for the mixed flow, which is a more conservative approach, then that is just N mixed flow is equal to 1 minus exponent of negative fractional value of your plug flow. And for the same system, I'm just going to change color just for emphasis. So for the plug flow here, mixed flow, for the 6.5 micron, 91.7%. So that's for the 10 micron size particles. For the 6.2 micron, the efficiency is equal to 0.652 or 65.2. So if we compare that here, so the plug flow is giving us an efficiency of about 98%. Mixed flow, we're getting much less efficiency, about 65.2. That's a much more conservative answer. For 5 microns, mixed flow would be 0.465. So about 46.5%. See, the difference actually decreases as your efficiency decreases. And for that 1 micron size particle, the efficiency of the mixed flow is, the live caption keeps getting in the way, is equal to 0.247 or 2.47%. So notice it's essentially the same. So as I said, when you're comparing the efficiencies of plug flow to that of the mixed flow, you're going to see a much greater difference for higher efficiencies than you will with lower efficiencies. Any questions about this problem? In 1951, Lapo developed a semi-empirical relationship between the size of the particles caught in the collector and the size that pass. So think of this as a strainer. You have particles that will be collected and some that smaller ones that are smaller than the diameter of the collector that will pass through. So Rambler developed an equation. It's later refined. It's referred to as the Rambler equation, and it provides what is referred to as a cut diameter. That's defined as the diameter of a particle for which the efficiency is 50%. widely used. It is on the Fae or in the Fae Reference Handbook. We'll look at some of those equations. So it is equal to 9. It's basically the same equation, just rearranged. And one of the things I didn't mention with all of these are also based on Stokes' law. Okay, so I didn't talk about that, but inherent in all of this is Stokes' law. So these are all developed for spherical particles. These images are taken from the Fae Reference Handbook. You see here the equation for that cut diameter. And if we look here, we take the ratio of the particle itself to the cut diameter, we can determine or estimate a collection efficiency based on this graph. And just recognize that it is a log-log plot. Now, the other equation that is used is this equation here, which provides the efficiency, but as a function of this ratio. Basically, all this equation is this plot, but it's as a function of the diameter of this cut diameter divided by the particle diameter. So dPc is the cut diameter and d sub p is the particle that you're looking at. And that provides an estimate of the efficiency. All of the material in the Fae Reference Handbook is all aligned with this figure here, which includes a plan view, so looking down at the centrifugal separator. Air enters, got a width, and then it's going to move inside and then out the center. Looking at an elevation view, this is the length of the body. So this is referred to as the body length. Below is the cone length. We've got the height of the inlet. So this we refer to as V sub I. Oh, sorry, W sub I. We have a diameter. We also have a diameter of the exit. And these will be, we'll use these in the next example. The number of turns can be estimated by this equation here. So H is your inlet height. L sub B is the length of the body that I just showed you right here. L sub C is the cone length. And that will give us an estimate of the number of turns that the gas stream is making as it moves down the cyclone. Typically, your number of turns will be around 5. This table is also from the Fae Reference Handbook. What it doesn't tell you is that these are actually ratios. And they're based on the body diameter. So the reference handbook doesn't mention anywhere that this is the case, but for all of these cases, the data that's given, the body diameter is 1, and the values that are given are a ratio. So for instance, if you use a 2-meter diameter body diameter, then your length, so let's say we've got a 2-meter body diameter. My body length will be what? For a high efficiency. For a high efficiency centrifugal separator, if diameter is 2, the body length is 2.8 meters. Okay. The inlet width would be 0.42 meters. And that's for high efficiency. So think of these values then as ratios, which is what they are. Okay. High throughput means that we're able to sacrifice efficiency in order to increase the volume or the flow rate of the gas. We don't need as high an efficiency. And if that's the case, then we can use a high throughput. So we have an example here. It's a more complicated example, and I thought I changed this. So we've got a conventional cyclone. It has a body diameter of 1 meter, airflow rate of 150 cubic meters per minute, temperature is 293 Kelvin, and 1 atmosphere. We have particles that have a density of 1,600 kilograms per meter cubed, and we have a size distribution that's shown below. So notice, not all of the particles are the same size. About 1% in mass of our particles are between 50 and 100 microns, and about 9% by mass of our particles are between 2 and 4 microns. So that means the removals are much more complicated in terms of calculating the removal efficiencies. So in order to calculate these, we need a velocity. So our inlet velocity is Q over HW, so the height times the width. And that is equal to 150 cubic meters per minute divided by the height, which is 0.5 meters, and times the width, which is 0.25 meters, and that is equal to 1,200 meters per minute. N sub E, the number of turns, is equal to 1 over H times L sub B plus L sub C, the cone length, divided by 2. And that is equal to 1 over 0.5 times 1.75 plus 2.0 divided by 2. All of the data here are from that previous table from the Fae Reference Handbook. And that is equal to 5.5. So we have 5.5 turns of the gas stream in the body of the centrifugal separator. The cut diameter is equal to 9 times mu W sub I over 2 pi N sub E, inlet velocity, times rho P minus rho G, all to the 1/2. And that is equal to 9 times 1.86 times 10 to the minus 5 kilograms per meter second, times the inlet width, 0.25 meters, divided by 2 pi times 5.5 times the velocity. We need that in meters per second. Do that conversion, times 1,600 minus 1.18 kilograms per meter cubed, and I apologize for all of the lines today, to the 1/2 power. And that is equal to 6.15 times 10 to the minus 6 meters. Your answer then is in meters, which is equal to 6.15 microns. So that's the cut diameter. That's the diameter for which 50% of the particles would be removed. So at 50% of the particles having a diameter of 6.5 microns would be removed by this centrifugal separator. We have a distribution of particles. So this is the data that you're given. We'll calculate the average diameter for each grouping. So this is just 0 plus 2 over 2, 2 plus 4 over 2, 4 plus 6 over 2. So it gives us our average diameter. And then we'll take the particle, the cut diameter, so it's 6.15 microns divided by 1, and that gives us this first ratio. Second one is 6.15. We'll divide that by 3. 6.15 divided by 5. So we'll calculate all of the ratios. We'll calculate the efficiency the same way that we calculated efficiency before. So this is identical to the way that we've calculated efficiency. And then our efficiency, we take our efficiency times the mass percent. That will give us the mass percent of that size particle that were collected. So this, okay, we have 0.03, we have 1%, we have 0.19, and we have 3%. I'm sorry, we have 9%. There. We have 0.4, and we had 10%. There's just a round off error in there. That's why the difference. And then if we sum all of these values, that gives us an overall percentage. If our temperature had been 350 degrees, okay, and everything else was the same, the only thing that changes is the viscosity and the density of the gas. And if that were the case, then the cut diameter would become 6.5 microns. So now 50% of particles that are 6.5 microns are removed. And the efficiency of removal of this particle distribution, given everything else is the same, the total removal would be 67%. So you can see as we increase temperature from 293 to 350, so it's about a 57 degrees Celsius increase. We see about a 2% decrease in efficiency by these calculations. So we'll stop there. On Monday, we'll finish this. We'll look at multicyclones. We'll look at the pressure differentials across these units, and we'll look at electrostatic precipitators. Happy to answer any questions. Question about the 67%. So that 67% was assuming everything is the same, except the temperature is 350 degrees Kelvin instead of 293. So that changes the viscosity, it changes the density of the gas. So given everything else constant, that would mean that we'd have a total particle removal of 67% as compared to the almost 69%. Have a great weekend and happy to answer any other questions.